So far, we have been discussing principles of methods of production of metals using pyrometallurgy, hydrometallurgy, electrometallurgy. We will now discuss some techniques of refining. In other words, we would like to go from impure metal to pure metal. Now, I think we should first be very clear as to what we mean by the word impurity. Theoretically speaking, there is nothing in this world which is totally pure. It is because we have no method of knowing if something is totally pure. According to Avogadro's hypothesis, 1 gram atom of anything will have 6 into 10 to the power 23 atoms, but our purity detection level, say in the chemical laboratory, will at most go to finding 1 in 10 to the power 9, that is 1 parts per billion. Now, that implies that 6 into 10 to the power 23 minus 9, that is 6 into 10 to the power 14. So many atoms in a gram atom will go undetected. So, if there were other atoms and many atoms, impurity atoms at this level, it looks very large, but it is below 1 part per million, 1 part per billion. So, we cannot detect. So, if we find something, we find it is absolutely pure according to today's analytical techniques, which is going up to 1 parts per billion, we should not think it is totally pure. There are other impurity atoms below that level, which we are not able to detect. Fortunately, with what we can detect, below that perhaps very often impurity levels are not important. As a matter of fact, we should say that an impurity is an impurity when it has an undesirable effect on the intended use. Consider for example, copper. Now, copper is a metal which is used in electrical applications. So, if you copper for electrical applications, there oxygen is a very serious impurity. It has to be less than 0.01% sometimes. Why? Because if you allow oxygen to be there, then the electrical conductivity is very badly affected. Some oxides will precipitate at the grain boundaries. So, oxygen is a serious impurity. Whereas, if we were to make a sculpture out of a copper alloy or copper in coinage, if there is some oxygen, it does not matter, because it does not affect the intended use. So, we always look at purity from the point of view of the question whether the impurity is affecting the intended use. If it is not affecting the intended use, we can ignore that. But then in many situations, we find that we have impurity elements which must be removed, otherwise we cannot use the metal for the intended use. Now, the first thing to know is that there are two basic approaches in refining, two basic approaches. In refining of impure, or sometimes we call it crude metal. Approach 1 is first produce bulk metal, that is impure, then purify. Now, the aim is, in the beginning the aim is to produce as large a quantity as possible, bulk recovery, and after you got the bulk recovery, then you worry about the impurity contents. In the second approach, right from the beginning we try to produce a pure compound, and which will automatically give pure metal. So, you see the two basic approaches, they are quite different from each other. What do we do in iron and steel making? We do not worry about producing pure iron, pure steel or pure anything. We just produce as much of iron as possible as pig iron. It has a whole lot of things, carbon, manganese, silicon, phosphorus, sulfur, whatever. We then go for steel making, a purified version of pig iron. So, you are first producing in bulk quantities, then you are purifying. Whereas, you will find there will be examples where we cannot use this approach. Right from the beginning, the aim would be not to produce metal in the bulk, but a pure compound. And once you got the pure compound, from there automatically the metal you will get will be pure. There are many ways of doing it, and we can say that purification can be achieved by chemical methods, or by physical methods. I will very quickly indicate some of these methods, and what I say I am going to say is not a total picture, but some of the important ones I would certainly mention. Under chemical methods, the most important method is fire refining. A method that has been used from time immemorial for thousands of years. Fire has been used to eliminate from the crude metal impurity elements or elements you do not want. Say for example, consider iron and steel. Simply by keeping it under fire in the molten state, or by injecting oxygen through that, we can remove carbon, silicon, phosphorus, manganese from iron. This is how pig iron is purified in iron and steel industry. From pig iron to steel, steel is a purified version of pig iron. We eliminate carbon, silicon, phosphorus, manganese as stable oxides by blowing oxygen, or in the open hearth furnace simply by keeping the metal for long hours under oxidizing conditions. The idea is to produce oxides of carbon, silicon, phosphorus, manganese, which preferentially form prior to forming of iron oxides. Of course, in the process the pool of metal gets very saturated with dissolved oxygen, which has to be removed later on by a process of deoxidation. That is a separate matter. Now, similarly, we can remove a whole lot of metals, lead, arsenic, antimony, tin, sulfur, magnesium, aluminum, iron, etc., from copper. Copper in molten state, we treat them under oxidizing atmosphere, and the impurity elements will form either volatile oxides or solid oxides, which will separate out as sludge. We can remove sodium from zinc, we can remove antimony, arsenic, tin, zinc from tin and zinc from lead, and there are many others. We can remove iron, aluminum, zinc from tin and zinc from gold. Now, in all these cases, the things that are being removed obviously are forming more stable oxides compared to the metal that you want to purify. When we come to discussing production and purification of individual metals, some of these will be repeated. We can also do sulfidation, means preferentially form sulfides of impurities as compared to the metal being purified. Copper can be separated from lead, copper can be separated from bismuth and tin, because this will form stabler sulfide as compared to the rest. A very effective way of removing impurities is through chlorination. We can remove zinc from lead, because if you have lead and zinc in the molten state, if you pass chlorine, zinc chloride will form, vapors will come out, lead chloride will not form when zinc chloride is forming. Zinc, copper, lead can be removed from bismuth, lead from tin, and other examples are there like this one, silver, copper, zinc from gold, etc. So, the basic principle in this sort of fire refining is very simple, that we are keeping the crude metal in the molten state under oxidizing conditions. We control the partial pressure of oxygen various levels. We can remove the impurity elements either as volatile oxides or as solids, which will come out as a slag, which will be skimmed off periodically. Very standard technique. The other methods of that will make use of chemical processing, of course, would be in hydrometallurgy precipitation. If everything is taken into solution, you can precipitate impurity elements as oxides or carbonates or sulfates or whatever. Then there are some special processes called ion exchange and solvent extraction. Exclusively used in hydrometallurgy, widely used in hydrometallurgy. I will discuss that little later. Under chemical methods of purification, one should also include electro-refining. There the idea is that in a suitable electrolyte, we will have the impure metal as anode, we will have a sheet of pure metal as cathode, and we will do electro-refining when this impure metal M will dissolve as M plus ions or whatever is the valency, and this will go and deposited on the pure cathode. So, with time this will begin to become thinner and this will become thicker. So, from an impure thick anode will produce a pure thick cathode. What will happen to the impurities that are there in the impure or crude metal? Two things can happen. From here, some impurities may dissolve in the electrolyte. This is the electrolyte. Some impurities will dissolve, some will not dissolve, but as the metal is taken out of this, they will simply drop as insoluble particles called sludge. So, two things can happen. We produce a pure cathode from the impure anode, impurities will be released, some will go into the solution, some will be deposited at the bottom as sludge. Now, both of them may be very valuable. We can recover byproducts from the sludge, we can recover some impurities if they have their uses from the solution also. So, these are some of the chemical methods. Now, before I go into solvent extraction and electrorefining, let me discuss a very interesting method which come under the class of vapor transport processes. Vapor transport process. This is not suitable for large scale production, but it is an extremely sophisticated technique for producing pure metals from impure metals, and it is applicable for many metals. But the reason I am discussing is it is based on a beautiful thermodynamic concept. See, whole idea here is that we will take the impure metal, make it react with a vapor or gas, say we call it vapor or gas 1, to produce another vapor 2, means that vapor which is the gaseous reactant reacts with the impure metal and takes it into a gas phase vapor 2 at some temperature T 1. This vapor is taken out and at another temperature T 1 can be greater than T 2 or sometimes T 1 can be less than T 2. This reaction is reversed, means we will regenerate the vapor 1, but now we will have pure metal. I hope you understand the scheme. We have impure metal and we create an intermediate gas phase vapor 2 using a gaseous reactant vapor 1, and then this intermediate gas phase that we have created is at another temperature which may be higher or lower decomposed to regenerate that vapor and produce pure metal. Obviously, this thing cannot be done in the same chamber. The idea is that once you have produced the vapor 2, you take it out into another chamber and then you decompose to get the pure metal, and this vapor of course, will be recirculated. In the system, there is no consumption of the reactant which is taking the metal into the gas phase. there is a very interesting example application of this in the case of purification of nickel. Now, that has a special name called carbonyl process, where nickel impure, solid nickel, is made to react with carbon monoxide, which is gas, at about 45 degrees. At such low temperatures, it can be converted to nickel carbonyl. This nickel carbonyl at a higher temperature, 240 degrees centigrade, decomposes and the reaction goes this way. So, you regenerate carbon monoxide and now you have pure nickel. It looks very easy, but such a process is very dangerous. Carbonyl is a very poisonous gas. Everything has to be done in a closed chamber. Similar reaction is applied in the case of aluminum, liquid impure. One can react with aluminum tetrachloride gas to form at 1000 degrees aluminum monochloride gas. So, using this gaseous species, we are taking aluminum into a gas phase and then this gas decomposes at a lower temperature to regenerate this and of course, pure aluminum. So, essentially at one temperature we produce an intermediate gas by gasifying this metal through a reaction with a gaseous species, and then the reaction is reversed at another temperature, which can be at a higher temperature or at a lower temperature. Now, a gentleman called Van Arkel achieved some similar things in around 1925, and it is called Van Arkel's process, very famous process, where impure tungsten solid is reacted with iodine gas. I am writing I because at the temperatures where the reaction is taking place, iodine is atomic to produce tungsten iodide gas. At another temperature, it is reversed. This method can be applied for in a small scale for many metals like beryllium, chromium, copper, iron, nickel, palladium, silicon, thorium, uranium, vanadium, zirconium, etc. This is the reason why I want to discuss it in a few minutes, because it is in a class of its own, a very interesting process. Some call it Van Arkel's process. We have the other names like carbonyl process for nickel, and in general they are called vapor transport processes, because we are transporting impure metal through a gas phase to a pure metal form. In these cases, we are taking the crude metal at a lower temperature and we decompose it at a higher temperature. Questions that come to our mind is, when will the temperature for the forward reaction T1 and temperature for the T2, when will T1 be more than T2 when will T2 be less than T1, when this is achievable, when this is not achievable, what are the thermodynamic conditions for that. I would like to discuss that. But before I proceed, let me show you this diagram. This diagram figure shows how purification of tungsten is done by Van Arkel's process. These are the two tungsten electrodes. This is a tungsten filament, and by passing current, this filament is kept at a high temperature. The rest of the chamber is at a lower temperature, but the filament inside is at a higher temperature because a current is passing through. This heat generated here may heat the chamber. If necessary, it can be heated from outside also. Now, iodine comes to this chamber separately, and we have a vacuum arrangement to maintain whatever pressure we want. What happens is that the crude metal is kept along the periphery in a cage. We have a molybdenum supporting grid, means there is a cage all around, but there are perforations. So, the gases can come and go. Now, in this case we have seen the temperature required for forming tungsten iodide. I have not given the temperature, but I will give it little later. It forms at a lower temperature. So, in this chamber tungsten iodide vapor will form, and when it goes and hits the filament, in this region it gets heated. So, pure tungsten is deposited, and then iodine vapor is rejected. So, the iodine vapor will keep coming here, react with to form tungsten iodide, move there, and it will get decomposed, tungsten will deposit. So, you transport tungsten from this cage to the filament gradually grows thicker, this filament grows thicker, and from here you lose crude metal gradually. Whatever impurities are there in the tungsten will be left behind in this place. Now, this is one design. Essentially, we are able to have in the same chamber two temperature zones. One zone is here, another zone is here, and the way it is done is very convenient, that the crude metal stays here and the pure metal grows at another place, and iodine is coming here, picking up tungsten from here, going there and getting dissociated the tungsten iodide, and it keeps going on, and that material goes. When we have got a very thick filament, we will cut it off, put another tungsten wire, and we will put more tungsten here, crude tungsten, and we will do the purification. Of course, it is a very schematic diagram. The rate of deposition will depend on many things. Rate of deposition, rate of deposition will depend on factors like geometry, arrangement of filament, with respect to crude feed. One has to optimize the distance between the filament and the crude feed, the dimensions of the chamber. It will depend on nature of feed material, it will depend on temperature of the vessel, at what temperature, you remember, it will depend on the pressure of iodine gas, that is maintained within the chamber, etcetera, etcetera, etcetera. Let us look at this reaction in little more detail. Essentially, the reaction is that a metal X, solid or liquid, is reacting with a gas Y. To generate an intermediate gas. This is the intermediate gas. Now, there are Y moles of gas giving only 1 mole of gas. In this side, we have more entropy, because the gas is disappearing in the reaction and creating less gas, we have less entropy. So, we have an entropy change in this, which is negative. Now, we can write for the forward reaction delta G naught 1 minus R T ln P x y y. We are dealing with two gaseous species y y. It is happening at temperature T 1 delta H naught 1 minus T 1 delta S naught 1. And for the backward reaction, we can similarly write ln P x y y P y y Now, I mentioned before that normally delta H naught, delta S naught values do not change with temperature. So, we can actually get rid of the notations 1, 2, etcetera. Is delta H naught minus T 1 delta S naught, delta H naught minus T delta S naught. Now, see kind of things we can derive from this simple looking at this simple thing. What we really want is that a situation like this. We need to ensure that the free energy change in the reaction or free energy change formation of the intermediate will go from negative to positive side. So, for the forward reactions, it should be below 0 in this direction, below this temperature. Beyond this temperature, this line must cross the 0, so that the reverse reaction becomes possible. You will recall that in the case of Ellingham diagrams, we had free energies of formations of oxides plotted against temperature. Basically, it was metal always in terms of 1 or 2, and we are writing 2 MO. The picture is somewhat similar. In this also, entropy is reduced because a gas phase on the left hand side disappears. So, there is an entropy change, and that is why all the lines move upwards, and I had always mentioned that this is the entropy term. Same thing here, the slope here will depend on the entropy term. So, basically you go back to the previous picture, the reversal of the reaction, whether we can go from in the forward direction and then at another temperature come to the left hand side, will depend on several factors. First of all, suppose there was no heat of reaction, if delta H naught was 0, then T 1, T 2, T 2, T 2 cancel out, which means the reaction becomes insensitive to temperature changes. If there was no enthalpy change, then it would not be possible to reverse the reaction at all, because delta G naught will not depend on delta on temperature anymore. Temperature will get cancelled out. On the other hand, if the delta H naught term was very large, then also will be a problem, because delta H naught actually is the intercept, also in Ellingham diagrams we had seen. It means, if the line was something like this, the temperature was so high that it was inconceivable that we will go to such a high temperature for decomposition. So, there is a restriction here, should not be 0, should not be too high. Interestingly, this is a critical term, because larger the slope of this line, the faster we will be able to reverse that. But if it is very shallow, then something we might have to go to very high temperature reverse, but if it is steep, then we should quickly be able to ensure reversal, and that will depend on the entropy change, which will depend on what kind of intermediate gaseous species you are making, you are able to generate. So, this is the equation, and as I have mentioned, if there is no delta H naught in the reaction, then T 1 would get cancelled out, and therefore, this term will not depend on temperature anymore, reaction becomes insensitive. This is critical. This will tell us how fast or how slow things can happen. Now, look at the actual data for reactions of tungsten chloride to form WCl6. This is for tantalum to put TSCl5. This is hafnium to form hafnium tetrachloride. Now, all these things can be impure metals can be purified by this method, form an intermediate gas, then dissociate it at a higher temperature to get pure metal and regenerate the halide. I am giving you data for chlorine, and these data are given for different pressures in the chamber. For 1 atmosphere lines, 10 to the power -3 atmosphere lines. Let us ignore that. Let us look at the solid lines only. You will find the slope is more, slope of the line is more for tungsten, because here 6 moles of gas are consumed to make 1 mole of gas. There is lot more entropy change, delta S naught is larger. In this case, 5 moles react with the solid to produce 1 mole of gas. In this case, 4 moles make 1 mole of gas. So, you see the changes in slope of these lines accordingly. It is highest here, it is intermediate here, it has the least slope here. So, we will try to ensure that we form intermediate gas that give us maximum change of entropy. Now, in these cases, because tungsten has a higher valency, the process becomes very effective for tungsten, because in temperatures below 1000 degrees, we can produce this gas. Just we go beyond 1000 degrees and the reaction is reversed. I hope you have understood the basic principle. I have given some data and you will find that same thing here, that the delta S naught value for tungsten 2W6 is higher than that for tantalum pentachloride, which is larger than that for hafnium. So, the delta S naught is the critical parameter. This also is important, because when this is small, like in the case of tungsten hexachloride, the intercept is small, means you are very quickly going to the you can quickly cross the 0 point in delta G naught scale. The larger it is, the farther away from that line that you have to cross. And of course, these are also important, the melting point parameters, because if tungsten, for example, had the melting point been low, then what would happen, that in the filament you will not have the solid depositing. You might get a liquid and the liquid will drop off, and you would not get a solid filament. You will have all kinds of problems. The fact is that it has a high melting point definitely helps in the kind of apparatus we have. So, there are all these parameters are important. Now, to show that the most important thing is the entropy parameter, let me just show you another slide here. As I said, we are bringing in iodine or chlorine gas, but we are writing in terms of Cl because of temperatures where we are forming the intermediate gas and the Cl2 dissociates. So, we can write the reaction as Ms NCl, giving you the intermediate gas where N can have different values for different metals. For this, we have an expression like that delta G naught plus RT ln K, and that RT ln K will have three terms, one pressure of this intermediate gas, ln P this divided by P Cl, and of course, activity of M, which is 1, we do not we can forget about that. If the pressure in the chamber is 10 to the power minus 3, we finally get an expression like this, and when PMClN intermediate gas is also in the chamber 10 to the minus 3, this will give the final expression. So, this gives us the slope, and entropy change in decomposition reaction given by N becomes a decisive factor, as you can see given by this reaction. Now, the dissociation temperatures for various metals are like this. For beryllium 800 degrees, chromium, copper 900, iron you can see, nickel, silicon, thorium, titanium, uranium, zirconium. Tungsten will decompose tungsten chloride 6 only at 1100 degrees. This is all for 10 to the power minus 3 atmospheric pressure, because if you change the pressure from this to that, then actually we are creating a problem for us. If we look at the solid line, this is for 10 to the power minus 3. Now, this is the solid lines are for 1 atmosphere and dashed lines are 10 to the minus 3. For solid line, this is if we have greater pressures, then we have a solid line, and if we have a reduced pressure, we have the dashed line. Now, if we operate at a very low pressure, you see you might have to go to very high temperatures for decomposition, whereas you will be able to do that at a lower temperatures if you had higher pressures. But there are many factors to be taken into account as to whether you should operate with high pressures or low pressures. Maybe we need not discuss it now, but this gives you the idea that you can do the reversal reactions over a wide range of temperature. One has to take into account kinetics of that process also, what will be better at high pressures, what will be better at low pressures. Now, there are some general rules for such transport processes. And I mentioned some of them. The first is that no transport is possible if delta G naught value is 0 or very small. If the enthalpy change for that reaction of formation of the intermediate gas phase is very small, then the process becomes insensitive. You cannot gasify the crude metal at one temperature and decompose it in another, because the equilibrium constant becomes independent of T. Again, if the absolute value of delta G naught is very large, then too there can be no measurable transport. Equilibrium constant becomes insensitive to temperature. Like if this is a very large value, then this term T 1 delta naught term becomes too small compared to this, and we will not be able to have the reversal. The sign of delta H naught determines the direction of vapor transport. Whether it is endo, whether it is exothermic will determine whether you will form the vapor at a lower temperature and decompose it at a higher temperature, or we will form it at a higher temperature and decompose it at a lower temperature. Like in the case of nickel, we form the intermediate gas carbonyl at a lower temperature around 40, decompose it at 240. But in the case of aluminum, we go through a reverse thing. Aluminum trichloride reacts with crude aluminum to produce aluminum monochloride at a higher temperature, and it decomposes at a lower temperature to regenerate aluminum trichloride and pure aluminum. So, you can see for yourself how it is done by, if you look at that equation, the sign will determine what will happen. Of course, for delta naught is not equal to 0, there is a delta H naught for maximum transport. There has to be a balance between the value of delta H naught, which is critically needed, otherwise you will not be able to have the reversal. There is a value of delta H naught for maximum transport to take place, and maximum transport effect increases as the absolute value of delta H naught increases. So, this is a brief discussion of the vapor transport processes. I discuss it in little more detail because thermodynamic principles are very interesting, and this process makes use of these thermodynamic principles, but it is not for a large scale purification of metals. Let me now come to two techniques called ion exchange and solvent extraction, who are extensively employed in hydrometallurgy for purification of leach liquor. In that case, we are not dealing with a solid impure metal and purifying it. The idea is to have the metallic values in a solution along with a lot of impurity metals as ions. We would like to selectively take out the metallic ions to produce a pure compound. from which we will produce pure metal. We are coming to the second approach in purification. Now, the ion exchange techniques makes use of some complex organic acids or bases which are insoluble in water. The salts that are formed because of reaction of this resin and a leach liquor, they are also insoluble in water. So, basically I am showing you one particular cation exchange resin here. There are many resins. These are all solid organic compounds, and the structure has basic or acidic groups which are capable of ionization and exchange reactions. Basically, what you see here is a large molecule that comprise of interconnected and cross-linked chains. It is a large molecule, there is cross-linking also, and there is interlinking like this. In this particular resin, this is the place where an exchange reaction will take place. Means this hydrogen will be knocked off, in that place a metal cation will be absorbed. So, when you have in the liquid many metals, one or two particular metal cations will be replaced by this hydrogen will be replaced by that, and then the metallic value that you are aiming at will be absorbed by this resin. Now, here what we are showing is a cation exchange resin, because this is where a cationic exchange will take place. We sometimes write it simply as R x, means resin matrix, and X is where the exchange will take place. R is the polymer backbone and X is the ion exchange site. Here the ion exchange site is SO3H, where the hydrogen will be replaced by the metal cation by some reaction such as this. Say copper sulphate solution is there, it comes in contact with this resin, we are simply writing as R SO38, because SO3, this is the part where the exchange reaction will take place. So, in the place of H, copper will go, H2SO4 will be created. So, there are two step process. The feed solution with metallic values will pass through the solid resin, unabsorbed impurity ions will pass off unabsorbed, but the metallic value will be absorbed in the resin, and then that can be washed or eluted through a process of washing or elution by fresh water, fresh acid. The resin will be regenerated and the solution will take out metallic values. Now, this is a very simple explanation, that basically what all we do, I'll come to that when I continue with the lecture. Let me now conclude this lecture. We started by discussing purification techniques for metals. We said first of all define what you mean by purity. Unless the presence of an impurity is affecting the intended use, it is not an impurity. And then there are different ways we can take out the impurity from a metal. One approach is produce the metal in the bulk and then purify, take out the impurity elements. The other is do not follow that approach, to start with produce a pure compound, and then from that you get the metal out. There are whole lot of chemical methods. I have discussed fire refining, sulfidation, chlorination, we have talked about intermediate vapor transport process. Then I have just started discussing ion exchange, which I will continue in the next lecture. Thank you very much.